Hello everyone, welcome back to my channel Electrical Concepts. My name is Avikan Roy. So in this video lecture we will discuss about time and edge domain analysis of RLC series circuit. So let's start. So as you can see, this is the circuit diagram of RLC series circuit, and V is the supply voltage and IT is the current flowing through that circuit. Okay. So first we will see the mathematical analysis behind that, and then we will discuss the time and edge domain response of this system. Okay. So as you can see, if you apply the KVL here, you will get this equation, and if you perform the Laplace transform on that equation, you will get this kind of expression, and Is is the Laplace transform of the current flowing through that circuit. So from here you can easily get the expression of the Laplace transform of current, and it is the expression of the Laplace transform of the current, as you can see. And now for further analysis we need to discuss about the characteristic equation. As you all know, in control system the standard form of characteristic equation in case of second order system is this, that means a square plus 2 zeta omega ns plus omega n square equals to 0, where zeta is the damping ratio and omega n is the natural frequency. So now if you compare this standard form with the characteristic equation of that system, that means this. So after comparing you will get these values. So omega n, that means the natural frequency will be 1 by under root LC, and the damping ratio zeta will be R by 2 into under root C by L. Okay. So now this is the roots of characteristic equation, or we can say pole of the system. Okay. So S1 and S2 are the two poles. If you perform the Sridhar Acharya rule in that standard form of characteristic equation, you will get this expression of the roots of that equation. Okay. So now we will see different cases like undamped, overdamped, okay, critically damped. As you all know, different cases are possible depending upon the value of zeta. So we will see one by one. So if I talk about the undamped case, that means zeta equals to 0. So if you see here, zeta will be 0 when your resistance is 0. That means the resistance in that circuit is absent. Then the system will behave as undamped system. Okay. You may also say that the zeta will be 0 if the C is 0. That is only true from the theoretical perspective, but practically it is not possible, because if you make the C to be 0, it means the natural frequency becomes infinite, which is not possible. So the only thing is that the resistance is 0, and that means your damping ratio of the system is 0, because we all know the resistance acts as a damping element in an electrical circuit. Okay. So in undamped case the resistance is absent, so the poles or the roots are completely imaginary, as you can see, plus minus j omega n, and here omega n is 1 by under root LC. So it is completely imaginary. So now if you increase the resistance from 0, then your zeta value will also increase. So when your zeta value is in between 0 and 1, we call it as underdamped situation, where as you can see the roots are complex conjugate. Okay. That means it has both real part and the imaginary part. So if you put the values of zeta and omega n, you will get this expression. If you further increase the zeta value, a certain point will come which is called as critically damped case, where zeta is equal to 1. And why is it called critical? Because it is neither underdamped nor overdamped, and here the poles are same and completely real. As you can see, there is no imaginary part present in that system, and zeta equals to 1, and both the poles are same, that is minus 1 by under root LC, which is also same as the natural frequency of the system. If you further increase your zeta, that means resistance, you will enter into an overdamped situation. Okay. That means zeta is greater than 1. Okay. And here as you can see both the poles are completely real, and they are not same, but they are real. Okay. So this is the actually mathematical analysis of RLC series circuit. So in my next video lecture I will discuss about the time and S domain response of that system. Okay, so I hope you have enjoyed this video, and please like, share, and also don't forget to subscribe to my channel. Thanks for watching and goodbye.